Dr. O here, and welcome to Chapter 10, the chapter on gases. So what are we going to be learning in this chapter? Well, we're going to start off by learning about kinetic molecular theory, and we're going to see those principles play out as we go through and study the gas laws. We're also going to learn about what creates pressure, what behavior or what quality or property of gas is creating pressure as we understand it. We're going to take a look at the simple gas laws, which will lead us into the ideal gas law. Then we're going to take a look at what partial pressure is, which is when you have a combination of gases and how they contribute to overall pressure of a gas. We're going to take a look at effusion, revisit some stoichiometry, and then look at real gas behaviors. So let's get started. When we talk about gases, one thing that we absolutely need to know about is pressure. So how does a substance that's in a gaseous state create pressure? Well, let's bring in an air tank, and the blue dots are going to be our air molecules. So what is one of these air molecules doing? Well, it's moving around and it's bouncing off the tank's walls. And every time it bumps into the wall, that air molecule is creating a push against the tank wall. Now, when it's only one molecule, it doesn't seem like much, but what if we double the action and we had two molecules bumping against the tank walls? Okay, still not that much, but a bit more. And what if we had all of the air molecules pushing against the tank wall? Well, now we have something worth noting. Now we can actually feel the pressure, the pushing of these molecules. And this effect, the result of many air molecules bumping into something such as the tank wall, this is what we call pressure. Now that we know what is creating pressure, we can understand how pressure can be influenced and manipulated in a particular situation. So let's do that. There are three postulates or assumed truths in the kinetic molecular theory. And the first one being that gas particles are small. So why does this matter? Well, let's bring back our air tank and have a look. So here's the tank and here are the air molecules. And you might remember from learning about states of matter that one of the characteristics of gases is that the molecules are widely spaced apart. In fact, they're so far apart that one gas molecule doesn't even know the other gas molecules exist. That's why I call the gaseous state the diva state. A gas molecule thinks it's the only one in existence and therefore it is the most important one ever. So how does this influence volume? Well, as we can see from this particular picture of our gas and in the air tank, the gas molecules themselves inherently don't take up very much volume because they're very small. And that's postulate number one, that the kinetic molecular theory is that gas particles take up very little of the volume of gas when you have a volume of gas. So most of the volume in a gas is actually empty space. Postulate number two states that the average kinetic energy of a gas is proportional to its temperature, which we measure in Kelvin. So let's bring back our air tank. And let's say that this tank is sitting in your car on a 70-degree day, and this may be what those molecules are looking like as far as their movement. Now let's say that you've been on campus all day and that a cold front has blown in and now it's freezing outside. What do you think those gas molecules are going to look like? How might they be moving? Well, they probably are moving a bit slower. There's not as much kinetic energy when the temperature is colder. So let's say that you decide to get out of the cold and you drive to Arizona with this air tank in your car where it's 110 degrees Fahrenheit outside. What do you think the gas molecules in your air tank are doing now? Well, these particles are going to be moving pretty frenetically. They're going to be pretty jazzed up because there's going to be more energy in this particular system. So with these three scenarios, we can see how the gas molecules are moving given the amount of energy in the system, in this case thermal energy or heat. The less heat, the less motion, the more heat, the more motion. Now previously we stated that the collective collisions that gas molecules create when striking a surface as they move about is what creates pressure. And with that in mind, in which of these temperatures will the tank have the greatest pressure? Well, that'll be the one with the most hits against the tank wall per given amount of time. And that would be the tank in the 110 degree temperature. And which tank will have the lowest pressure? Well, it'll be the one with the fewest hits against the tank wall. So what we have here is that we have the same amount of gas in each tank. The tank is the same size, but we've been able to manipulate the pressure in the tank by changing the temperature of the gas, which gives credence to postulate number 2 of the kinetic molecular theory. Now, before we move away from postulate number 2, let's look at the actual equation for kinetic energy when we're talking about gases. And it's 1/2 times the mass of our particle times the square of the velocity that the molecule is traveling. So what does this mean to us? Well, given that gases come in different sizes and therefore different masses, it means that different gases will travel at different speeds provided that kinetic energy of a system is held constant. So let's say that we had a tank filled with hydrogen and neon gases. Can we predict which one of these will be moving faster and which one will be moving slower? Well, let's look at an example. So here we have hydrogen. Hydrogen comes in at 1.08 atomic mass units. Neon comes in at 20.18 atomic mass units, about 20 times that of hydrogen. And if we had a system where our kinetic energy was held constant, let's say maybe at 200 joules, then we could calculate using the kinetic energy equation that the velocity that hydrogen is traveling is about 608.58 meters per second. That's pretty quick. Now, how fast could we say that the neon would be going in the same system where we have kinetic energy equal to 200 joules? Well, using the kinetic energy formula, we could do the calculation and we would see that neon is only traveling at about 140.79 meters per second. So this gives credence again to the idea that larger particles move slower and small particles move faster when you have a system with a certain amount of energy in it. Now, the third postulate has to do with something called elastic collision. So what's that? Well, a picture's worth 1,000 words. So let's start by having a look at a collision as most of us understands collisions, which is a car crash. So here's a collision, and what we see are 3 cars in motion, and then there's an impact. And then what happens? Well, all 3 come to a stop. So ask yourself, where did all the energy of forward motion go? Because each car was going at a particular speed and there's a fair amount of mass there, so it had a fair amount of kinetic energy to it. Well, it went into the crunching metal, breaking glass, friction against the asphalt as they all came to a stop. So basically what happened was the energy of their motion got transferred elsewhere in the system. So in this collision, once there is an impact, energy gets drastically altered to the point that nobody is even moving forward anymore. And there is therefore a substantial loss of energy as a result from this system. This is not an example of an elastic collision. This is a static collision. So now let's have a look at an elastic collision. So this is an example of an elastic collision, and what do you see? Well, you see the cue ball hit the other balls, and then suddenly most of the other balls are in motion. So what happened here? Well, again, energy was transferred from the white ball to the yellow balls. That is, no substantial energy was lost in this system due to collision. And this is the nature of an elastic collision. And this is what happens to gas molecules when they fly about and collide with each other on various surfaces. The motion doesn't stop. It just gets transferred elsewhere within the system. And ultimately, there's not a big loss of energy out of the system as a result of collisions. So from our new gained understanding of elastic collisions, from our example with the pool balls, the third postulate of kinetic molecular theory states that because the collisions of gas particles are elastic, the energy of the system is transferred but also preserved. So to recap in brief, the first one says the particles are small, because gas particles are small, which means that most of the volume of gas is empty space. The second thing is that the average kinetic energy is proportional to temperature. The greater the temperature, the greater kinetic energy. The less the temperature, the less kinetic energy. And number 3, that the collisions that gas particles experience are elastic in nature, which means that the energy of the system is maybe transferred within the system, but it stays within the system and ultimately is preserved. Now, we already know that pressure is a result of the gas molecules colliding with the walls and with each other. As in our case of our air tank, they're colliding with the walls, or maybe if you're just standing out in the open, the air molecules could be colliding with your skin. And because we're in chemistry class, we need to have a formula and some units in order to express pressure, and we're going to do that with this formula, where we say pressure is going to be equal to the force of the gas over a particular area the gas occupies. Now, common units for measuring pressure are going to be millimeters of mercury. Here we go, millimeters of mercury, the torr, atmospheres, these are abbreviations, and Pascal. And of course, there's going to be relationships between these units, such as 1 millimeter mercury is going to be equal to 1 torr, and 1 atmosphere is equal to 760 millimeters of mercury. So it's good to have these handy because you'll be needing to do some sort of inner conversion. I believe in some of the homework problems, or you may have something being given to you in torr or millimeters of mercury, and you'll probably have to convert it into atmospheres. So it's good to have these noted somewhere in your notes. Now, when we had the example where we had the air tank in the car and we drove from a snowstorm in New England to a hot sunny day in Arizona, we saw the effect of temperature on gas. And we learned that the greater the temperature, the greater the pressure in the air tank. And so there was a proportional relationship between temperature and pressure. But what role does volume play in pressure? Well, in this case, there is an inverse relationship between volume and pressure, and we could write it like this if we wanted to put it in a formula. So let's bring up an example of what this might look like. So for comparison, we have our regular air tank, and we could say that gas particles are moving like this. And if we had a smaller air tank, it could be looking like this. Now, in the smaller air tank, each gas molecule has less distance to travel before it strikes the tank's surface. So each molecule is striking the tank's surface more times in a given time period than what we see happening in the larger tank. And we know that pressure is created by the gas molecules colliding with the tank's surface. So the more times the gas molecules hit the wall, the greater the pressure. So from our example here, we can see that when we have the same amount of gas in both tanks, when the volume decreases, we're going to see an increase in pressure, which is a demonstration of the inverse relationship between volume and pressure. When one goes up, the other one goes down. And for the larger tank, the reverse is true. We have an increase in volume, a larger volume, which means we're going to have a lower pressure. Okay, so we've looked at the roles that temperature and volume play in influencing pressure. What role do you think particle density plays? That is, the number of particles. Do you think that the number of gas particles actually affects pressure? Well, yes, it does. That's why we're going to talk about it. The number of particles, or the moles of particle, is going to be proportional to the pressure. That is, the more gas particles there are, the greater pressure there will be. And we could write that like this. So let's look at an example. So here's our tank with our particular number of particles. I believe there are 7 blue dots representing our gas particles moving around in here. But what if we had the same size tank, but this time we had 14 particles in there? Well, we know that pressure is created by particles colliding with the tank walls. Therefore, the more particles, the more collisions, and the more collisions, the greater the pressure. So with an increase in the number of particles, that is an increase in the number of moles, because that's how we count particles, is in moles, we're going to see an increase in the pressure. And the same is true for the tank with fewer particles. When there are fewer particles, there's going to be less pressure. So we saw at the beginning of the lecture how temperature affects pressure, that at 70 degrees the particles are moving at a particular speed, creating a particular pressure, but at a higher temperature the particles are moving faster and are therefore creating more collisions and therefore creating a higher pressure. So from this we can conclude that temperature and pressure are proportional, and that is the greater temperature we have, the greater pressure we're going to have, and the opposite is true, a lower temperature, less pressure. So what are the simple gas laws? Well, they're the first discoveries that demonstrated the interrelated nature between the 4 basic properties of gas, which are pressure, temperature, volume, and moles. Now, these contributions were made by three of the scientific greats, Robert Boyle, Jacques Charles, and Amedeo Avogadro. So let's have a look at what these three characters discovered. So Robert Boyle was an Englishman and a scientist and a bit of a smarty pants, and his research shows us the relationship between volume and pressure, provided that the temperature of the system remains the same, as do the number of particles. So as a result of Boyle's work, we know that volume and pressure have an inverse relationship, meaning that as one property gets larger, the other gets smaller, and we could write a statement like this. So volume and pressure have an inverse relationship. So here let's look at an example. So let's say that we have the four properties, and Boyle's law requires that moles and temperature remain constant, that their values don't change. Now, if we were to decrease the volume of this system, what we would also see happening is an increase in pressure. So how could we write this as a formula? If this is our current system, we could write a formula like this, where P1, V1, these are our values of pressure and volume in our current system. Now, when we change the pressure and the volume, we could write our new values like this. We could say it's P2 times V2. And the interesting thing about this is that the values of the first measurements are equal to the second measurements. So P1 times V1 is equal to P2 times V2, and this is Boyle's law. Now, Jacques Charles's research shows us a relationship between volume and temperature, provided that the pressure of the system remains the same, as do the number of particles. And as a result of Jacques Charles's work, we know that the volume and temperature have a proportional relationship, which means that as one property increases, the other one gets larger too. And we could write a statement that's about like this. And if we look at the demonstration of this law, here we have our four properties, and Charles requires that we hold the pressure and the moles constant, that is, they stay the same. And what we would see is that as we increased the temperature, we would see an increase in volume. Now, not surprisingly, this guy was a hot air balloonist, so good for him for writing his observations down and giving us this law. So how could we write a law about this particular observation? Well, let's have a look. Now, if this is our current system, we could write the initial values of volume and temperature like this. We would say that initial volume over initial temperature, V1 over T1. And these are the volume and temperature of our current system. And when we change volume and temperature, we could write our new values like this. We would have V2 over T2. Now, the interesting thing about this is that the value of the first set of measurements, that is V1 divided by T2, is actually equal to the value of the second set of measurements, which is V2 over D2, or T2, and this is Charles's law. In addition to hanging out at his castle and figuring out how to weigh gas and coming up with this famous number, Avogadro's research showed us that there's a relationship between volume and moles, provided that the pressure of the system remains the same as does the temperature. As a result of his work, we know that volume and moles have a proportional relationship, meaning that as one property gets larger, the other gets larger too. And we could write a statement like this. All right, so let's look at a demonstration of that law. So what we need pressure and temperature held constant. That means their values don't change. Now, if we were to increase the number of particles, the moles of the particle, we would also see an increase in volume as well. So how is it that we could go about writing this formula? Well, let's have a look. If this is our current system, we could write volume and moles like this. We would say that the initial volume over the initial moles has this value. Now, these are the values of volume and moles in our current system. And when we change those, we would write our new values like this. We would have final volume over our final moles. And the interesting thing about this is that the value of the first set of measurements is going to be equal to the value of the second set. And this is how we write Charles's law.